I have a little bit of a talk before we jump into the meat and potatoes of today. So we actually have a couple of different options here. So these are what my thoughts are of what I would like to do, and then tell me whether or not you want to go along with this plan. And I'm legitimately open to suggestions. Looks like I need to turn the projector on. So last Wednesday, you were supposed to review some effectively basic MOSFET physics stuff, except that I had never bothered to post it because I got busy and forgot. So I was thinking we were going to start with that today and try to cover as much of that today, if at all possible. And then once we have a review of our MOSFET physics, then we would do a brief review of MOSFET amplifier circuits, just basically the single stage amplifiers and maybe a cascode as well. And then we have two paths. One path is that we go from our review of single stage amplifiers to effectively larger integrated circuit MOSFET building blocks, current mirrors, and all that kind of noise, which we're definitely going to have to cover / review. Or we could take a divergent path that would lead us through something that I think is new to all of you guys, the study of noise in transistor circuits, and how that affects our decision-making process with regards to how things are laid out. And then we move on into the IC building blocks and work towards finishing up our op-amp design and all that kind of stuff. So the question here is essentially, do you want to take the time to learn about noise or not? Race is generally shaking his head yes, but not vocalizing anything. Gavin, your thoughts?
I have a question. So like, I mean, I know noise is like one, but how relevant would you say?
So noise is an extremely relevant thing to at least understand where it's coming from and all that kind of good stuff, especially as you make your devices smaller and smaller and smaller, noise becomes more and more prevalent. That being said, it's not necessarily required for you to know to understand basic design concepts, but having an understanding of noise is useful, because you're going to be able to look at things and recognize, oh, well, this was done to mitigate flicker noise, or this was done for this purpose and all that kind of stuff. And as we go into splitting things up like we've been doing, so talking about implementing wide width transistors by connecting several in parallel, which would be done for matching purposes, you have to see what the drawback of that is. And it's the principal drawback of that is effectively the noise contribution from all of those pieces of silicon acting as thermal noise generators and what effect that has on your system. I think it's valuable, but I also understand that it is difficult. And you're not going to be losing out on something huge if we don't do it, or you're not going to be gaining something huge if we do it, but it is absolutely pertinent to IC design. So I'm giving the option to you all.
I don't want to put it as going down the path of least resistance, but do you really want to have extra trouble? That's not to be rude.
Yeah, no.
Important topic.
Did you cover that in like previous videos?
The only time I ever covered it was last year, which was the only time the students ever thought this class was any good, but I've only taught it 3 times, so.
I think it'd be nice to be able to see the video just to.
Okay, I can put it up if you wanted to go through all that kind of stuff. Okay. All right, so let's start our offset stuffs. Okay. So what Gavin was last. So the first thing we're going to do is talk our way through the physics of how these guys behave. And to kick that off, we're going to be talking about our threshold voltage first. So let's consider first an NMOS device where we have our P-type substrate. We have our thin field oxide layer like so. And then we're going to have, oh gosh, what colors did I use? I'll just use green for all these because they're all going to be implants. So we're going to have an N plus implant here, an N plus implant here. The P plus implant over here. Here we have our polysilicon gate. And we're starting off with something fairly straightforward. Our source terminal is going to be grounded. Our body terminal is going to be grounded. Our drain terminal is going to be grounded. And our gate terminal here, we're going to have some voltage VG that is applied. Okay. So when VG is greater than 0, what's going to happen? Well, the gate polysilicon and substrate form a parallel plate capacitor. So as the voltage VG increases, what we are going to observe is that some positive charge, let's call it Q plus, is going to accumulate at the gate, and in turn, some negative charge, Q minus, has to accumulate in the substrate underneath the gate, right? Because if we have a fixed voltage drop across this capacitor and we allow things to come to steady state, the charge on the top plate has to equal to the charge on the bottom plate. There's going to be equal and opposite. So where the positive charge comes from is pretty straightforward. We have a voltage source whose positive polarity terminal is connected to the gate node. And so effectively electrons from the doped polysilicon move to the positive polarity terminal of the voltage source, leaving behind a net positive charge in the polysilicon. Where does the electrons for the negative accumulated charge directly underneath the gate come from? So from the body terminal to some extent, sure. So in this case, we have a P-type substrate, which means our body is electrically neutral, but it has more holes than electrons. So when VG is small, we are going to be able to pull those minority carrier electrons into that space. So effectively, we would be pushing holes away from this region in order to sustain the electrons that we have underneath the gate. And our charge needs to perfectly balance out, right? Well, that positive gate terminal, or excuse me, that positive potential at the gate pushes away holes, leaving behind an ion-filled depletion region with no charge carriers, right? So effectively, once we push all of those holes away, we have the ionized carriers giving us our net negative charge there, okay? As we go beyond how far we can push our holes away, right? Because this is a function of an electric field, and we know that the strength of the electric field gets smaller as a function of distance squared or distance cubed. I don't remember. I think it's distance squared.
Sounds right.
Yeah. So effectively, there's going to be some finite point at which we don't really get a lot more. We can ramp the voltage up, but we're not going to see a lot more of our ability to push those holes away. And that's at the point where we're going to start drawing electrons from our body in. But at some point, we're going to run out of those minority carrier electrons as well. So let's talk about things here really quickly. So when VG is greater than 0 and small, the positive charge at the gate pushes holes away. I'm going to put in parentheses here. Towards the body terminal. What I really mean is just into the bulk. Leaving behind a thin region let's call it of ionized acceptor, sorry, because this is a p-type substrate. Acceptor atoms. So we would have something like this. Those are our ionized acceptor atoms. Polysilicon gate.
Those are all negative.
Yes, because the holes have been pushed away, so all that has to be negative charge there. I'll make a note of that. Ionized acceptors. We have positive charge here. Negative charge here. Okay. So as the gate voltage increases, the E field established by this parallel plate capacitor drives more holes away from between the source and drain implants. And draws minority carrier electrons through the depletion region. To form channel. So this statement is associated with this picture. So effectively, we put a small amount of charge on the positive plate. We're able to draw or uncover a small amount of negative charge in that depletion region, right? We can't actually really do anything there though, because all of that negative charge that's associated with those ionized dopant atoms is immobile, right? Because those aren't free valence electrons able to move or anything like that. Those are effectively stuck there. All of the bonds and all that kind of good stuff are still intact. It's only when we make our gate voltage even larger that we start sweeping in free electrons, not a whole hell of a lot of them, but free minority carrier electrons into that region and establish our channel. And so that's going to look something like going to have a layer of negative charges, and then they're on the opposite side of the depletion region as the bulk is. Here's our body. I made that ground symbol too large. Here's our source. Here's our drain. And our voltage VG is much greater than 0 because it's on the order of a volt-ish. Okay. This process called inversion because the area of the substrate directly beneath the gate is gaining the opposite type of free charge carrier. Strong inversion occurs when the region below the gate becomes as N-type as the substrate is P-type. So we can describe this relationship mathematically, where the threshold voltage VTH is defined as phi ms plus twice phi f plus the square root of 4q epsilon of silicon times the magnitude phi f times the substrate dopant concentration, all divided by the oxide capacitance. Okay. So we need to talk about what these different things are. So this is the threshold voltage. This is effectively the potential that's applied at the gate to cause strong inversion to occur. Phi ms is the difference in work function between the metal, and this is our polysilicon gate, and our semiconductor, which in this case is our P-type substrate. Two phi f is the contact potential of the substrate mathematically given as kBT over Q times the natural log of N sub over the intrinsic carrier concentration. And that leaves us with this stuff over here on the right that we're going to talk about here, okay? So threshold voltage is obviously a voltage, okay? The difference in the work functions is also going to be a voltage, okay? So effectively, that difference in the work functions is usually going to be pretty small, but it's representing effectively the amount of voltage necessary to rip an electron from those bonds and move it up to the vacuum level, okay? 2 phi f is the contact potential, so that's similar in a sense to the built-in voltage, and the equation kind of bears that out. It's got something to do with the Einstein relationship times the natural logarithm of the dopant concentration over the intrinsic carrier concentration. If it were a PN junction, this would be NAND over NI squared, right? It also represents a voltage here. So what we have on the right-hand side is this big thing under a square root sign divided by capacitance. Because it's added to voltages, that total thing must represent the voltage as well, or a voltage. So if we have voltage is equal to something over capacitance, what does that something have to be? Charge, exactly right. So this big ugly thing right here is literally just the charge stored in the depletion region. That's it. Charge stored in the depletion region divided by the oxide capacitance gives us the voltage difference across the depletion region. And then we have to take into account the contribution of our free charge carriers, which is where our contact potential comes from. And then we have to take into account the difference in work function of the metal to semiconductor junction, which is effectively telling us how much our bands bend to accommodate all this thing if we were looking at an energy band diagram, okay? So this tells us what size of voltage we have to apply to overcome all of the different things and force strong inversion to occur, all right? So this is where our threshold voltage number comes from. And depending on our process, it can range from anywhere from 0.3 volts all the way up to a couple of volts. Because we have multiple different polysilicon layers, as I mentioned earlier, we could have different contact potential or different threshold voltages. And the reason for that is largely because this Cox value is going to be different if our polysilicon layer that we're using as our gate contact is further away, physically further away than the substrate, okay? So let me ask you guys a simple-ish question here, or I hope it's a simple question. But what does it mean that I have exceeded, if my voltage applied at my gate is greater than or equal to the threshold voltage? What it means is I have free electrons in the area between the source and the drain. Does it mean they're moving in any particular direction? No, not at all, right? It just means I have the ability to conduct, but not that I am actually pushing current in one direction or the other, okay? So now let's talk about body effects. So let's say that we have a transistor. Here's our P plus region, N plus, N plus. Here's our poly. Our source and our drain are still grounded. Our voltage VG is greater than 0, so that we are pushing holes away. But our voltage VB is less than 0. So our body potential is lower than that of our source potential in this particular case. Okay. So we know that holes are going to be pushed out from the region beneath our gate due to the fact that VG is greater than 0. Okay. Well, if VB is less than 0, we are going to start attracting holes towards the actual body terminal, which is going to leave behind a larger depletion region. So if the width of the depletion region is getting larger, what does that mean about this charge stored in the depletion region? It's also getting larger. So if we scroll back here, if our threshold voltage is dependent on the amount of charge stored in our depletion region, and we have figured out a way to cause our device to store more charge in the depletion region, what is happening to our threshold voltage? It's going up. So the body effect, if we allow our body to be at a lower potential than our substrate, we are going to increase the threshold voltage of our device. So now our threshold voltage is going to look something like this. VTH naught, where this is our normal threshold voltage, plus gamma times the square root of 2 phi f plus VSB, where this voltage VSB is a DC voltage, so I'm using capital letters for my subscripts, minus the square root of the absolute value 2 phi f. This gamma is our body effect coefficient. It is equal to the square root of 2q epsilon Si times our substrate doping level over our oxide capacitance per unit area. and typically ranges from 0.3 square root of volts to 0.4 square root of volts. So in most of the stuff that we did in 335 and 336, we were dealing with discrete components, okay? So in a discrete transistor, typically the body terminal and the source terminal are literally fused together. In a integrated circuit, that is not necessarily the case unless we specifically design it to be so, okay? So we will probably wind up observing body effects playing roles in some of the circuits that we are going to be analyzing. Okay. All right. So we understand where the threshold voltage comes from. We understand now what kind of tends to mess with it. Now let's talk about the IV characteristics of a MOSFET. So let's consider a semiconductor bar carrying a steady current. We just have a bar with a rectangular cross section. Like so. And the current of I is flowing through it, okay? If the linear charge density along the direction of current is QD, measured in coulombs per meter. And the velocity of charge movement is V, measured in meters per second. And our current I is simply QD times V. Now let's apply this observation to the transistor. And I am going to attempt-ish to draw a 3D-like structure to explain some of these dimensions here. So I'm going to apologize in advance for how shitty this is going to look. So here we have our substrate, our very thin field oxide layer, body. This is going to be our source. This is going to be our drain, and So I can give it some, attempt to give it some depth, so to speak. All right, so this guy right here is our body connection. Let's say that it's grounded. This guy right here is our source, also grounded for now. This guy right here is our drain that's grounded. And here is our gate terminal, where we have VG is equal to VTH, such that we have free negative charge available for conduction between our source and our drain. So since the onset of inversion occurs at VG equal to VTH, the inversion charge density produced by the gate oxide capacitance must be proportional to VGS minus VTH. So let's unpack that statement there, okay? The onset of inversion occurs at VG is equal to VTH. The inversion charge density produced by the gate oxide capacitance must be proportional to the difference in the voltage there. So effectively, we are going to have some net charge that gives us some constant value of QD, right? If we were to increase VGS, any excess charge that's placed on the gate has to also occur in the channel. So effectively, for every positive charge we place on the gate beyond inversion, we have to pull a negative charge from somewhere. And so from this, so let's see, so if VGS is greater than VTH, any charge placed on the gate must be mirrored in the channel, yielding a uniform charge density of QD is equal to W times Cox times VGS minus VTH, where the W dimension is this distance. So I'm going to take a copy of this. And we're going to talk about what happens when we start applying voltages. All right. So let's say that we put a voltage at the drain. I should have moved that further. Edit, undo. So if we let this voltage VD become greater than 0, what happens? Well, we should observe that since the potential across the channel is now non-uniform, the charge density should also be non-uniform. So effectively, let me erase some of this, and I'm going to try to encapsulate this with this line. So this is telling us effectively where the edge of our channel is at. Okay. As VD increases with respect to VS, channel potential varies as a function of position across the channel, yielding a local voltage difference between the gate and the channel. Which varies from VG on the source side to VG minus VD on the drain side. From this, the charge density at any point along the inversion layer channel can be written as WRI as a function of position is equal to W Cox VGS minus V of X minus VTH. Where V of X is the channel potential as a function of position. So this is our X direction. This location is 0. This location is L, all the way across the channel. Okay. So the current that flows from the drain to the source, obviously opposite electron movement, is given by ID is equal to QD times V, which we discussed earlier, which is just going to be negative W C ox VGS minus V of X minus VTH under voltage V, where the negative sign comes from the fact that positive current occurs in the opposite of electron flow, right? So we're for a semiconductor, our charge carrier velocity is given by our drift equation. V is equal to mu times E. And recognizing that E is equal to negative dV by dx, our current becomes positive W Cox VGS minus V of X minus VTH. Is that correctly? Mu E, the electron mobility. Have we been doing E or N?
I think we did N a couple times, but I think,
Just trying to be as consistent.
I think that might be the first.
Okay, well, let's make it no longer the time that we've seen the E at all then. So this is what our drain current looks like. Now we're just going to do algebra and calculus to get an equation here. Okay. So multiplying both sides by dx and integrating both sides. So we're going to have ID times dx is equal to the integral of mu n W C ox multiplied by VGS minus V of X minus VTH dV. So for our current integral, this is an integral of position, right? So we're starting on the left-hand side from the source, which has a location of X is equal to 0. And we're integrating over to the other side of the channel where X is equal to L. For our integral of this dV thing, we're looking for effectively the potential difference across this thing, right? So we are going to have 0 volts on the left-hand side and a voltage VDS on the right-hand side. So if we're integrating from the source side to the drain side for our distance, then the voltage of the source with respect to the source is 0, right? There's no difference between those two, to the voltage measured at the drain with respect to the source, which is going to be some non-zero number. And what this is going to yield is ID is equal to UN Cox W over L times VGS minus VTH times VDS minus 1/2 VDS squared for the constraint that VDS is less than or equal to VGS minus VTH. And if we repeated this where our drain voltage was large, such that we pinched off our channel, we're skipping a couple of things here, but again, this is a review, right? So let's talk about this number right here. So here we are assuming that VD is greater than 0, but also that VD is less than VG, and we get this nice line. Once VD exceeds VG, we have something that looks like this, very, very exaggerated, but effectively our channel becomes pinched off. And if we perform this exact same integration that we just did, we wind up getting ID is equal to 1/2 UN Cox W over L VGS minus VTH quantity squared. Okay. And this is for specifically VDS is greater than or equal to VGS minus VTH, yielding curves that look something like this. So here is our drain current. Here is VDS. Make sure I'm drawing this correctly. Something like this, where we have this parabolic thing right here. Each of these corresponds to different levels of VGS minus V. So this would be, scroll down here, VGS1 minus VTH. This value corresponds to VGS2 minus VTH. Value corresponds to VGS3 minus VTH. What we're observing here, what I'm attempting to show you guys here, is that once VDS exceeds this thing, effectively our current flattens out. Now we know that's not fully true because we're aware of a phenomenon called channel length modulation, which we'll talk about here briefly. But effectively, on the left-hand side here, we have operation in the triode region. And on the right-hand side of that parabolic arc that I did in gray, we have saturation region operation. And our device behaves differently depending on which side of that parabola we're on. Okay. So we are going to be talking about amplifiers. And the amplifiers that we are going to be talking about rely on our transistor's ability to turn a voltage at the input into, so a voltage at the gate terminal into a current flowing through the drain terminal, okay? And that relation is best described by what's called the transconductance of the device, which I appear to have misplaced my page of notes. So I go straight from 8 to 11. So we will stop here today, talk about transconductance at the beginning of the class next time, because I don't want to accidentally screw anything up. And then we'll get into small signal models and start talking about our amplifiers and all that kind of good stuff. All right, so we've gone all the way through current voltage characteristics. So we'll do channel length modulation and transconductance on Wednesday. Already. Sure. I desperately need to turn, oh geez Louise. So I left you back a while back, I'm sorry. Desperately need to turn these into PowerPoints.